So let's move to sensitivity report. In the sensitivity reports, you can see two sections. The first section is about the variable cells, and the second section is about the constraints. And in the variable cells, you can see the decision variables and their final value, which are the optimal value of the problem when we when solve them using the solver, and the current value of the objective coefficient in the objective function of the linear program model. And then you can see two more columns at the end of the tables. One of them is the represent the values that we can increase the coefficient objective values, the coefficient of the objective values in a specific range. For example, I can increase the value of the objective function of the first variables by 100 and decrease it by 50 units. If I do so, given that the other constraints, the other parameters are fixed, then the objective value is not going to change. This means that even though the slope of the level curve is changing, but the optimal value, optimal solution of the problem is not going to change. So this is the range that still the value that we got, these values for the decision variables is going to stay constant. In the second one, we see constraints, and we have three constraints for this problem, and it has final values and shadow price and right hand side, and then the value that we can increase and decrease. The final value is the left hand side, the value of the constraint itself, and then right hand side is the constraint, the value, the b's that we have, the value of b1 to b2 and b3. Pay attention that if the final value and right hand side constraints are equal, that means that this constraint is binding, the similar way that we saw in the answer report. So you can see that final value of the first constraint and the constraint right hand side is equal. So that means this constraint is binding. And also the second constraint, because the value of the final value and the right hand side are equal, that means this constraint also is a binding constraint. And then we have a shadow price that we are going to talk in a moment, but this basically shadow price means that if I increase the right hand side by 1 unit, if I increase it by 1 unit, I'm gonna get objective function increased by this value. Notice to the sign of these values. If these signs are positive, that means if I increase the right hand side by 1 unit, I'm gonna get this much value increased to my objective function. So let's test this one on the solution of the problem that we already solved. So this is the optimal value of the parameters that we have, and the set of the problem is exactly same as the optimal solution that we got for this problem. So let's increase the first constraint by 1 unit and see how much is going to increase our total profit or objective value. So I increase it from 200 to 201, and you can see that the objective function has increased from 60,100 to 66,300. So that means 200 has been increased to the total profit. So this is the value of the shadow price. So basically shadow price means that if I could increase 1 unit of the resources by 1 unit, if I increase it, how much is gonna improve my profit? You can see the second constraint has a smaller shadow price. That means the first constraint has much more effect on the objective function. And then we have set of the constraint, set of the values that we can increase or decrease the objective function, uh, 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 the constraint. So we can increase the first constraint by 7 unit and decrease by 26 unit. This basically says that if I increase right hand side in this range by 7 units or decrease by this much, I have a change on the objective function 200 units whenever I change 1 unit. If I have a 2 unit change in the right hand side, if I increase 200 into 202, then I'm gonna have 2 times 200 as a increase in the objective function. Or if I decrease by 3 units and make it right hand side 197, then I'm gonna have 3 times reduction in the objective function. Similarly, we have the same range for the second constraint, but pay attention to the third constraint, that is the shadow price is 0. Comparing the final values and the constraint right hand side, you can see that this constraint is not binding. We had a similar conclusion in the answer report 1, that the third constraint is not binding. So this means that if I increase in this range, I will not get any increase in the objective function or decrease in the objective function. So any change within this range, if I increase right hand side by this unit, I'm not going to get any change on the objective function. So remember that shadow price for non-binding constraint is always 0, and change of the right hand side of the non-binding constraint in this range, in the allowable range, is not going to change the objective function's value. Shadow price has a very important information for us. Let's say we want to introduce new product for this company, and the product is going to take 1 pump, 8 hours of the labor, and 13 feet of the tubing. So we want to decide whether this adding this product is helpful or not. So it's going to take 1 pump and 8 hours of the labor and 13 hours of pumping. So in this case, the cost associated with adding this new product is going to be 200 times 1 plus this times this. So the basically shadow price is going to give you adding a new product to this model. So if I add all of this cost, it says if I add a new product to this model, the cost with this new product is going to be $333.34, because it's going to take 1 unit from this product and 8 units from this one. So total cost of the producing new product is going to be this much. If the profit of the new product is less than this value, then introducing a new product is not feasible. That means that's not worthwhile. So if the value is more than this, let's say it's the profit associated with this new product is 350, then that's a profitable product and we can have that. So this is the value that this shadow price provides us more analysis about the situation, the problem we are dealing with. So this is very important information. So we talked about every columns in this sensitivity report, but we haven't talked yet about the reduced cost. Basically, reduced cost is difference between the marginal profit, the profit that 1 unit of each product make, minus the resource that this product consumes. For example, take product 1, x1. The objective value of this product is the coefficient of the objective value is 350, and it uses one from the product, one pump and 9 labor hours and 12 tubing. So if we multiplied each of these values by the shadow price, we are going to get these values. So if we add all of these values, we get so if we add up all of these numbers, we get this value 350. And then if we take the difference of the objective coefficient minus this value, objective value minus this value, we got 0. So essentially means that the difference between the profit that makes this product and the materials that use this product is 0. Basically, when we have parameters and the value of the parameters are in the range, that means, for example, x1 and x2 we defined as they have to be positive, and then the maximum value that they can take is a positive infinity. And because their value is in this range, the reduced cost associated with these parameters is 0. Basically, if we have a maximization problem and the value of the parameters are between upper and lower bounds, then the reduced costs associated with these parameters are 0. But if they are on the lower bounds, the value of the reduced cost is going to be negative, and if they are on the upper bound, then that's going to be positive. But if the type of the problem is the minimization, then the sign of the reduced cost on the simple lower bound and the simple upper bound is going to change. It's going to be reverse of the maximization problem. But the variable, if the variables is between the lower and upper bounds, still the value of the reduced cost is going to be 0. Now we want to investigate the change of the constraints coefficient. Let's say, let's consider example. The company wants to introduce new product, which they use 7 hours of the labor and 13 hours of the tubing, and it use 1 pump. So we want to check whether producing this new product is profitable or not. To do so, we need to compute the reduced cost, that is the profit that this product makes minus the cost of this product. So the cost associated with this product is the 1 unit pump, which is multiplied by 200, which is the cost associated with this product pump. So in this example, the shadow price of the pump is 200, and then we have shadow price of the second constraint is associated 16.67, and 7 of them use this new product, and the shadow price of the third constraint is 0, and this product is using 13 of them. So if we calculate this number, we get a positive number. That means that producing the new product is profitable, so we can produce this product. But let's say we are looking for maximum, we want to find one of the parameters, we want to change one of these parameters of the constraint, one of these coefficients that makes this product feasible. For example, let's say we are looking for maximum number of hours that makes this product profitable. Let's say still this product use one pump, and we are looking for a number of the labors that needs to make this product profitable, and still it's using 13 hours of the tubing. So to do so, we just need to find the reduced cost, which is the reduced cost is the profit that this product makes minus the cost associated with production of this cost. So 320 is the profit that this product makes, and minus, because it used one pump, it's the reduced cost of the pump, the cost associated with shadow price of the pump is 200, so we have minus 200 minus shadow price of the labor is 16.67. so we are looking for maximum hours that if this product consume, that product becomes feasible. By solving this equation, we got 7.2. so if this product is profitable as long as this product needs 7.2 hours or less for producing each 7.2 hours of the second constraints, which is a labor, then it's going to be profitable. Otherwise, this product is not profitable. So far we talked about changing one of the coefficient of the objective function and the remaining the rest constant. So let's do a little change and change two of the parameter at the same time. Pay attention to the reduced cost of the C1, X1 and X2, which both are 0. So let's say I change this one within the possible range. So I increase this one by 50 units, which is in the feasible area of this range that I'm allowed to increase by 100 units. And then let me increase the second one by 20 units. So I'm increasing this one by 20 units. And you can see still the objective function, the optimal values are exactly the same as the one that we already solved. So right now the coefficient objective of the original coefficient objective was 350 and 300. But right now I changed to 400 and 320. But still you can see the optimal values are exactly same as the original problem. Now we want to, so this is not a coincidence, this is not a random thing. Basically when we change the coefficient of the objective function, multiple coefficient at the same time, we have two general scenarios. One is that all of the coefficients that we are changing, they have the reduced cost of the 0, like the x1 and x2 that we already changed. But the second scenario is that some of these parameters may have a non-zero reduced cost. Generally, when we have a reduced cost of the 0, all of the parameters that we are changing, the coefficient of the objective function that we are changing, if the changes are within the allowed range, right now for 350 is between, I can increase by 100, decrease by 350 by 50. So if I change the coefficient of the x1 and x2 in the given range, then the value of the optimal x1 and x2 is going to be same. This is guaranteed that if I change all of the parameters within this range, it's going to stay same. But whenever I have a reduced cost of the non-zero, then the situation is going to be a little different. In that case, we have to compute this equation. So ij here represent the values that I'm allowed to increase, like the one that we had here. This is 100 for this parameter. So for, let's say, if this is j equal to 1, then I of this one is I1 is going to be 100. And then we have another terminology here, dj, which is the maximum that I can increase. So dj d1 for the associated with the x1 is 50, and for the second one is 66.67. So delta Cj represent the change in the coefficient that Cj, the second Cj. So let's say I'm changing this objective value to 400. So 400 minus 350 represent the delta Cj, which is going to be 50. So positive 50. If I reduce this 350 to 250, then this is going to be minus 100. So whenever we change any parameters, if I increase it, I need to divide it by ij, the value that I'm allowed to increase. And whenever I reduce the Cj, I have to take the minus Cj, minus delta Cj over the value that I'm allowed to increase. And then, because either one of these cases happens, I have a value for Rj. If the Rj is less than 1, that means the objective function that the value of the optimal solution that we are going to get is going to be stay same. So that's guaranteed. Whenever we change for multiple coefficients, we just need to get Rj of each of the parameters based on this equation. If we are increasing, I have to divide the value, the value change on the Cj over the Ij, or if we are decreasing the Cj, we have to get the minus of delta Cj over the Dj and add them up. If the summation of Rj is less than 1, then the current solution remains optimal. But if it's greater than 1, then there is no guarantee. But however, it may remains optimal. So, but there is not anything guaranteed in that case. So if the summation of the Rj is positive, more than 1, that means nothing is guaranteed to be optimal anymore. Excel Solver provides one more report, and that's the limits. So you solve the model, and in the report section, just select the limits, and a new worksheet is going to open up, like limit report 1 here. So basically, this limit report has two sections. One section is that reports the objective value, and then the value of each decision variables and their optimal value. And also, one more interesting thing is that in this report you can see if we set one of the parameter, how much we can decrease another parameter. So lower limit, this column represents the value that we can reduce given that fix the other one. For example, if we fix this 78, then we can get 0, and this 78 and 0, that means x1 is 0 and x2 is 78, satisfy all the constraints, and the objective result is going to be this much. So remember that 350 was the coefficient of the first objective function, and 300 was the coefficient of the second one. So if I multiply this value by 0 and then multiply this value by this number, I'm gonna get this one. And similarly, you can put the 0 for this one, for the second decision variable, and 122 for the for the first decision variables, and you are gonna get this objective value. The upper limit is sets this one parameter at the optimal value and try to increase that. So obviously we are not going to be able to increase these values, and because these are the optimal solutions that we have.